So, welcome to talk number 5. Talk number 5 is about the idea of the ether. Quick recap from the last talk. So, last time we talked about the idea of light and matter being the same thing, that matter could be made of light wrapped into loops, and therefore light is moving energy and matter is stored energy, and that crucially time therefore is mapped out in matter, not in space or space-time, and that time slows down for you in your matter as you move through space. Therefore, everything appears to be relative, but it's not, or it might not be. So, in this talk, we're going to have a look at the idea of the luminiferous ether, which I like to think of as an invisible universe jelly. This is an idea that the entire universe is filled with a sort of invisible, stretchable, or vibratable substance, that you can't see it, you can't touch it, but that it fills all of space. So this idea, it comes from thinking about waves and the idea that light is a wave, and all the other types of waves that we have to have some kind of medium to travel through. So waves are an oscillation of the water in the ocean, but you have to have the water in order to have the waves. You can't just have the waves on their own. The waves have to have a medium, because the wave is a vibration or an oscillation of that medium. So waves in the sea must have water, and sound waves must have either air or some other medium to travel through. Obviously, sound can travel through solid things like walls, but whatever it travels through, it needs something to travel through, which is why in space, nobody can hear you scream, because there is no medium for those vibrations to travel through. So early scientists thought, what is the medium of light? If light appears to be waves, and it seems to behave like waves, sometimes behaves like particles too, but it certainly behaves like a wave, then what is the medium of light? And so this is where the idea of the ether came from, that in order for starlight to get to Earth, either from the sun or from another star, there must be some kind of medium which is vibrating or oscillating for those waves to travel through. And the idea came up long before James Clerk Maxwell. Newton talked about it before him, other scientists talked about it before him, but James Clerk Maxwell really took the idea and incorporated it into his theory. So he's famous for his experiments with electricity and magnetism. And he said, well, not only does light appear to be a wave, and light is probably the same phenomenon as electricity and magnetism, he also said, if you try pushing two same poles magnets towards each other, or rather the same poles of two magnets towards each other, they push each other apart. So there must be something between them. And it works in a vacuum. You don't need air between them. So it's not just pushing the air. So he said there must be something between these magnets. There has to be something there. And so he incorporated the idea of the ether into his theories of magnetism. But people thought, how do we detect this substance? We've got this invisible universe jelly. This is someone in a swimming pool of jelly, which I just thought was appropriate. But how do we detect it if we can't see it? We can't touch it. Does it even exist? Can we do an experiment to see whether or not it exists? So back in the late 19th century, two people called Mr. Michelson and Mr. Morley did an experiment to see if they could detect the ether. And this has been called the most famous failed experiment in history. So I'm going to go through what the experiment was, how it worked, and its surprising result. I should also note at this point that I'm spelling ether sometimes with an A, sometimes without an A. People seem to spell it either way. I used to spell it without the A, then I realized it looked like a typo of either, so I put the A on the beginning, and this presentation has a total mix of the two with no consistency at all. So before we get into the experiment about the ether, I want to do a little quick detour into waves, which is going to become relevant later. So this is just a bit of a reminder from a previous talk about wave superposition. So on the left, you've got two waves at the top, and you can see that they are in phase. So the peaks and the troughs line up with each other. And therefore, when those two waves combine, they combine into a bigger wave. The peaks and the troughs add together, so you just get a resulting larger wave. And then on the right, you've got destructive superposition, where the waves are out of phase with each other. So the peak of one lines up with the trough of the other, and hence when you combine them, you get nothing. And there are more complex interactions. If those waves were kind of a quarter of a wavelength apart rather than half a wavelength, you get some kind of weird looking wave. If they were different frequencies, you get a whole other complication. But essentially, constructive and destructive superposition, depending on what proportion of a wavelength they are out with each other. That's our quick detour done. Back to the experiment. So Albert Michelson and Edward Morley in 1887 devised an experiment to see if they could detect the ether. And their theory went like this. You have the sun and the earth is traveling in an orbit around the sun at about 29 kilometers per second. So the earth is traveling through the ether. The ether, if it fills all the universe, must be static. We've kind of lost the idea that the earth is the center of the universe. So the earth is traveling through the ether at high speed. The earth is also rotating, and that will become important too. But the speed of the earth's rotation is pretty slow compared to its 29 kilometers per second whizzing through space. So they devised an experiment, which was this. You have a light source on the left, and that shines a beam of coherent light, i.e. a single frequency of light. And that light hits a semi-reflective mirror in the middle, meaning that some of the light carries on straight through over to the right, and some of the light bounces at 90 degrees up to the mirror at the top. So then the light going up to the mirror at the top bounces back off and comes back down again. And it then meets up with the light which is bounced off the mirror on the right, which then comes back to the center. Some of that light then coming from the right bounces off that mirror and goes down, combining with the light coming from the top mirror going down, and comes down and hits the light detector at the bottom. So essentially, we're just sending two beams of light which have come from the same source and sending them on two paths at 90 degrees to each other, and then detecting the resultant light at the bottom. This experiment happens on Earth, and Earth is whizzing through the ether at 29 kilometers per second. So that means that the light traveling up and down is traveling with the ether, and the light traveling left and right is at 90 degrees to the ether. So they said, can we detect a speed difference in the light? Because some of the light is traveling with the moving ether and against it, and some of it is traveling at 90 degrees to it. So to think about what actually happens here, I've attempted a diagram. So the light source comes from the left and it hits the semi-reflective mirror in the middle, and some of that light bounces off and goes upwards. But because we're moving upwards on this page, by the time the light reaches that mirror, the mirror is further away. So the light has a longer path to travel going upwards. But then as it comes back down again, the semi-reflective mirror in the middle, where it recombines with the other light beam, has also moved. So this light source that's traveling parallel to the movement of the Earth has a longer journey on the way to its mirror, but a shorter journey on the way back. So that difference in journey time or journey length is sort of cancelled out. It will take it longer to get to its mirror, but it won't take it as long to come back again. So that traveling is just sort of, it all cancels out. It's a zero-sum difference. Now, when I first came across this experiment, I thought, well, surely the light going left and right won't be affected either, because it's just going left and right. But I hadn't thought about it properly, because what actually happens is this, that the mirror on the right is moving forwards as well, and therefore the light traveling left and right actually has to take two diagonals in order to make its journey. And then those two light beams recombine and come back to the light detector, which obviously has also moved. So the question is, are those two journey lengths the same? And therefore, should those two beams of light return to that light detector at the same time? I guess this question could be more accurately posed as, assuming that the ether is static and that light is a wave traveling through the ether, and therefore light travels at a constant speed relative to the ether, not relative to the Earth, should we detect a difference in when those light beams come back? Should they return at the same time? And if you go into the maths, do a little diagram properly labeled, apologies, this experiment is drawn the other way around, it's flipped through 90 degrees. And you label all the things and you make up some variables to represent all the different lengths and bits of time. You do some maths, which I'm not going to go into, but I will link to it. The maths is not that complicated. You do all the calculations, and the answer is no. Those beams of light should not return at the same time if there is an ether. There should be a difference between when they come back. That difference depends on the speed of the Earth, possibly depends on the distance of the mirrors, but essentially you should see a difference. There should be a detectable difference in when those light beams return. That's what I've just said. So then the question becomes, how do we detect that difference? The speed of light is really, really, really fast. And even if we could make this equipment huge, it would be really hard to time the difference. So how do we detect the difference? Well, we come back to our detour from earlier and we detect the phase difference in the light. So if the beams return at the same time, those photons will be in phase with each other, and so we'll just get a bigger photon or a more energetic photon coming back. And if the beams return half a wave period apart, they'll be out of phase and they will cancel. But more accurately, if the beams return at a different time, but that time is a whole number multiple of wavelengths, then they will be in phase. And if the beams return at a not whole number multiple of wavelengths, i.e. they're half a wavelength out, then they'll be out of phase and they'll cancel. And now we want to bring in the rotation of the Earth. So here's our equipment stuck on planet Earth. This is meant to be a top-down view of Earth, as if you're looking at the North Pole. The Earth is rotating around its axis, and therefore at some time later your equipment will be over here at 90 degrees. And so what will happen is, whatever the phase difference is to start with, that phase difference will change as the Earth rotates. So it doesn't matter whether the phase difference of the light to start with was a whole number of multiple of wavelengths or not. Whatever that phase difference is will change 6 hours later when the Earth has done a quarter rotation. And this is also crucial because it means that you don't actually have to get your mirrors to be exactly the same distance apart. It doesn't matter if you haven't made your equipment perfectly accurately. You'll have some kind of phase difference to start with, and you'll have a different phase difference afterwards. And if you can detect that phase difference, you have detected the existence of the ether. This is a photo of the equipment that they used. I think this is a giant piece of stone somewhere, possibly underground, to avoid vibrations and interference and things. I think they laid it on they like floated it on a bed of mercury, I think, to try and make it as level as possible, and so that it could essentially be sort of untouched and not interfered with anything. So this is their giant piece of equipment, and you can just about sort of make out the half mirror in the middle, and then the detector and the other mirrors in the corners. So this is their experiment, and the result was nothing. They detected no phase difference whatsoever, and they repeated their experiment, and no matter how many times they did it, they did not detect a noticeable phase difference when their equipment rotated with the rotation of the Earth. And so the conclusion was there is no ether. This idea that it had existed for hundreds of years, that the universe is filled with this invisible jelly, was put in the bin. So Isaac Newton had talked about this. He talked about the ether, other scientists as well, but he's one of the famous ones. James Clerk Maxwell had talked about it in his theory of magnetism. And then the Michelson-Morley experiment said there is no ether, conclusive proof that it does not exist. But what wasn't clear was, well, then what is happening? And it wasn't until sort of about 20 years later that Einstein came along and brought his theory of special relativity. And special relativity didn't necessarily explain what the medium was that light was traveling through, but it did explain that everything is relative, and therefore there cannot be a static ether in the universe, because the ether would have to be moving differently depending on which perspective you looked at it from. So when special relativity came along, it really started like a whole new era of science, and we are still in that era today. And it is science based on the idea that there is no ether, and there cannot be an ether, because everything is relative, and there cannot be a universal static rest frame in the universe, which is what the ether would require. And so the next 118 years of science have been based on Einstein's theory and have worked with the idea that there is no ether. And that is the end. No, only joking. It's not the end. Of course it's not. Let's have a look again. So an idea that Einstein incorporated into special relativity is the idea that objects contract when they move at high speed. This was not Einstein's idea. It came from Lorentz before him, and Lorentz developed the maths of Lorentz transformations, which also apply to Lorentz contractions. And it's this idea that objects traveling at high speeds contract in the direction of motion, and that their length contraction is proportional to their speed. So that means if we have a look at our equipment again, and the Earth is traveling at 29 kilometers per second through space, it's actually shorter. The equipment is contracted in the direction of motion. And that means if you redo the maths, taking into account the Lorentz contractions, you get a slightly different set of equations. And when you re-ask the question, what difference should you expect in the wave phases? The answer is nothing. So actually, when you take into account all of special relativity, including the Lorentz contractions, the result that Michelson and Morley got is exactly the result you would expect if there was an ether. It doesn't prove that there is one, but it certainly doesn't prove that there isn't. The result they got is exactly what you would expect if there was an ether. This is a picture of Richard Feynman, and this link, if you want to screenshot it, is the link that contains all those equations that I put up. The equations make a lot more sense if you read them with his explanation. The maths is not particularly tough. And at the end of it, he says this: it was ultimately recognized, as Poincaré pointed out, that a complete conspiracy is itself a law of nature. Poincaré then proposed that there is such a law of nature, that it is not possible to discover an ether wind by any experiment. So essentially, the universe covers its own tracks. If there is an ether, we can't detect it because any experiment that you can devise to detect it gets sort of twisted by the universe or contracted by the movement. And there is nothing that we can devise that will detect the existence of the ether. And so then talking about relativity, which was really the final nail in the coffin of the ether, as we looked at last time, it's possible that everything's not relative, it just appears to be. If time is actually not part of space-time that you move through, but time is something which happens in matter, then we can see, just like with the ether experiments, that nature covers its own tracks and it makes it look as if everything is relative, even though that's not necessarily the case. So if we take this idea that the ether experiment cannot detect the ether because nature tricks us, and everything appears to be relative because nature tricks us, then actually it's perfectly possible that the ether idea is still alive. And I will leave you with a quote from this guy. Nikola Tesla said, "Light can be nothing else than a sound wave in the ether." Maybe he was right. Maybe he wasn't. But next time, we'll take this idea a bit further and ask the question, is matter just vibrations of the ether, just like light might be vibrations in the ether? And now that really is the end.